Section: Introduction. In this section, we explore the concept of parameter-efficient fine-tuning, PEFT, for large language models, LLMs. PEFT is a technique used to customize these models for specific tasks by adjusting only a small portion of the model's parameters, as opposed to updating all parameters in full fine-tuning, FFT. One popular PEFT method is low-rank adaptation, LoRA, which enhances performance by updating parameters using low-rank matrices. These matrices can be combined with the original model parameters, reducing computational costs during inference. Various methods aim to enhance LoRA for LLMs, with most evaluating their effectiveness based on tasks like glue or instruction tuning. However, the use of different settings and datasets in these evaluations can make it challenging to compare their progress. Our study provides a comprehensive evaluation of LoRA across tasks like instruction tuning, mathematical reasoning, and continual pre-training under consistent settings. We observe that while LoRA performs well in instruction tuning tasks that focus on format interaction, it struggles in tasks requiring knowledge enhancement through fine-tuning. This limitation may stem from its reliance on low-rank updates, which hinder its ability to store new information efficiently. To address this, we introduce MoRA, a method that utilizes square matrices instead of low-rank matrices to enable high-rank updating while maintaining the same number of trainable parameters. MoRA outperforms LoRA in memory-intensive tasks and shows comparable performance in other tasks, highlighting the effectiveness of high-rank updating. Additionally, we discuss non-parameter operators in MoRA to adjust input and output dimensions for the square matrix, ensuring seamless integration back into LLMs. Our contributions include introducing MoRA, evaluating it across various tasks, and showcasing its superiority in memory-intensive scenarios. Section Summary. In this section, we introduce the concept of parameter-efficient fine-tuning, PEFT, as a method to adapt large language models to specific tasks by updating only a small portion of the model parameters, such as with low-rank adaptation, LoRA. While LoRA excels in tasks like instruction tuning, it struggles in tasks requiring knowledge enhancement due to its reliance on low-rank updates, leading us to propose MoRA, a method using square matrices to achieve high-rank updating within the same parameter constraints, outperforming LoRA in memory-intensive tasks and showing comparable performance in other scenarios. Section: Fine-tuning with LLMs. In this section, we explore fine-tuning with large language models, LLMs. Despite the strong performance of LLMs within context learning, there are situations where fine-tuning is still necessary. We can broadly classify these scenarios into three types. The first type is instruction tuning, which aims to better align LLMs with specific tasks and user preferences without significantly increasing their knowledge and abilities. This simplifies handling various tasks and understanding complex instructions. The second type involves complex reasoning tasks like mathematical problem solving, where general instruction tuning may struggle with multi-step reasoning. To enhance the reasoning skills of LLMs, most research focuses on creating specialized training datasets using larger models like GPT-4 or restructuring questions along a reasoning path. The third type is continual pre-training, which aims to boost the domain-specific capabilities of LLMs. Unlike instruction tuning, this type requires fine-tuning to enhance domain-specific knowledge and abilities. However, most versions of LoRA mainly use instruction tuning or text classification tasks from glue to demonstrate their effectiveness on LLMs. Since instruction tuning requires less fine-tuning compared to other types, it may not fully reflect the performance of LoRA variants. Recent studies have started using reasoning tasks to better evaluate their methods, but the training sets used are often too small for LLMs to effectively learn reasoning. For example, some methods use a training set with only 7.5K samples, which is much smaller than the 395K samples used by the state-of-the-art method. This small training set leads to poorer performance on reasoning tasks, making it challenging to assess the effectiveness of these methods. Moving on to the analysis of the influence of low-rank updating, the main concept of LoRA involves using low-rank updates to estimate full-rank updates in fast Fourier transform, FFT. LoRA utilizes two low-rank matrices to calculate the weight update delta W, where these matrices are denoted as A and B by decomposing delta W into BA. The rank of the weight update in LoRA is significantly lower, typically denoted as R, compared to the full-rank updating in FFT. While low-rank updating in LoRA performs well in tasks like text classification or instruction tuning, it tends to show weaker performance in tasks requiring complex reasoning or continual pre-training. Based on these findings, we propose a hypothesis that low-rank updating is effective in leveraging the original knowledge of LLMs to solve tasks but struggles with tasks that demand enhancing the knowledge and capabilities of LLMs. To test this hypothesis, we compare LoRA and FFT in terms of memorizing new knowledge through fine-tuning. We design a task where the LLM needs to generate corresponding universally unique identifiers, UUIDs, based on input UUIDs, with the knowledge required solely from the training data. We conduct experiments using Llama 27B as the base model, adjusting batch size, epochs, and learning rates for LoRA. The results show that low-rank updating in LoRA finds it challenging to memorize new knowledge compared to FFT, even with increasing the rank. However, for tasks like instruction tuning that introduce new knowledge, LoRA performs similarly to FFT with a small rank. This suggests that LoRA can effectively utilize the original knowledge of LLMs through fine-tuning, akin to FFT. Section Summary. In this section, we explore fine-tuning methods for large language models, LLMs. We categorize fine-tuning into instruction tuning, complex reasoning tasks, and continual pre-training. LoRA, a method using low-rank updates, shows comparable performance to full-rank updating in tasks like text classification, but struggles in tasks requiring enhanced knowledge and capabilities of LLMs, as observed in complex reasoning scenarios. Section Method. In this section, we introduce a new method to address the challenges posed by low-rank updating. Our approach focuses on maximizing the use of trainable parameters to increase the rank in delta W. We start with a pre-trained weight W_0 in R, D times K. Our method, called LoRA, employs two low-rank matrices A and B with a total of D plus K, R trainable parameters for rank R. By utilizing the same trainable parameters, we introduce a square matrix M in R, hat R, times hat R, where hat R equals L floor SQRT, D plus K, R floor, which can achieve the highest rank possible given that R is much smaller than both D and K. To achieve this, we need to adjust the input and output dimensions for M. We define two non-parameterized operators, f_text comp R, K right arrow R, hat R, and f_text decomp R, hat R, right arrow R, D, to decrease the input dimension of X from K to hat R, and increase the output dimension from hat R to D, respectively. These operators should execute in linear time based on the dimension. Additionally, we introduce corresponding functions, f_overline, text comp R, hat R, times hat R, right arrow R, hat R, times K, and f_overline, text decomp R, hat R, times K, right arrow R, D times K. To transform M into delta W for any input X, we ensure that delta W equals f_overline, text decomp left, f_overline, text comp left, M right. If this equation holds, M can be expanded losslessly to delta W using f_text comp and f_text decomp. This allows our method to integrate back into the LLM like LoRA. We explore various methods to design f_text comp and f_text decomp. One approach involves truncating the dimension and adding it in the corresponding dimension, which can lead to information loss during compression. To enhance efficiency, we propose sharing rows and columns of M among predefined groups G and G. This sharing strategy can be particularly effective for larger ranks such as R equals 128 or R equals 256, where only a few rows or columns in delta W share a common row or column. However, for smaller ranks like R equals 8, reshaping X instead of direct compression can help preserve input information. This reshaping incurs additional computational overhead but is beneficial for smaller ranks like 8. Inspired by rope, we further refine our method by incorporating rotation operators into f_text comp to enhance the expressiveness of M in distinguishing different segments of X. This modification enables M to differentiate between various parts of X by rotating them. Section Summary. In this section, we introduce a novel method to address the challenges of low-rank updating by leveraging the same trainable parameters efficiently. Our approach involves using low-rank matrices with shared rows and columns to enhance compression and decompression processes, enabling lossless expansion of matrices. By reshaping input data and incorporating rotation operators inspired by rope, we can improve the expressiveness of matrices and achieve efficient differentiation between input segments. Section: Experiment. In this section, we evaluate our method on various tasks to understand the impact of high-rank updating. We compare our method with LoRA and FFT on memorizing UUID pairs to showcase the benefits of high-rank updating. We also replicate LoRA, LoRA variants, and FFT on 3 fine-tuning tasks: instruction tuning, mathematical reasoning, and continual pre-training. We conduct experiments with different hyperparameters and methods to assess the performance of our approach. By using a single matrix instead of 2 matrices, we can initialize it directly with zeros. Grouping adjacent rows or columns together helps in training, and our method demonstrates significant improvements over LoRA in memorizing UUID pairs. Furthermore, we apply our method to 3 fine-tuning tasks for large language models: instruction tuning, mathematical reasoning, and continual pre-training. We select high-quality datasets for each task and evaluate the performance of both LoRA and our method. In instruction tuning, we use a dataset containing filtered samples and assess performance in 0-shot and 5-shot settings. For mathematical reasoning, we enhance capabilities using specific datasets and evaluate performance accordingly. In continual pre-training, we adapt the model to biomedicine and finance domains using relevant datasets. We compare our method with various baselines and implementations across different tasks. Each method is evaluated based on its performance and effectiveness in fine-tuning tasks. We present the results and analyze the performance of each method on the tasks, highlighting the strengths and weaknesses of different approaches. Our method shows competitive performance with LoRA on instruction tuning and mathematical reasoning tasks, while outperforming LoRA in continual pre-training tasks due to its high-rank updating capability. Section Summary. In this section, we evaluate our method on various tasks to analyze the impact of high-rank updating. We compare our method with LoRA and ReLoRA on tasks like memorizing UUID pairs and fine-tuning tasks such as instruction tuning, mathematical reasoning, and continual pre-training, showcasing the benefits of high-rank updating in improving memorization and performance across different domains. Our method, MoRA, demonstrates significant improvements over LoRA in memorization tasks and outperforms LoRA in biomedical and financial domains for continual pre-training, highlighting the advantages of high-rank updating for learning new knowledge efficiently. Section: Pre-training. In this section, we explored the impact of high-rank updating by training a transformer model from scratch on the C4 datasets. We used a specific model architecture with various components like RMS norm, SWI-glue, and rope on different dataset sizes. Our hyperparameters included steps, batch size, sequence length, and rank values for LoRA. We compared our method with LoRA and ReLoRA, focusing on the difference between high-rank and low-rank updating. To address the issue of high-rank updating, we introduced a method called MoRA, which combines merge and raint with LoRA to increase the rank of delta W. We encountered a challenge where directly merging certain parameters did not change the final rank of delta W. To overcome this, we adjusted the parameters post-merging to ensure an increase in the rank of delta W. Our experiments showed that MoRA outperformed LoRA and LoRA in pre-training, demonstrating the effectiveness of high-rank updating. By analyzing the singular values of delta W, we found that MoRA and ReMoRA had a higher number of significant singular values compared to LoRA and ReLoRA, indicating the success of our methods in increasing the rank of delta W. Furthermore, we investigated the impact of decompression and compression functions in MoRA on the GSM-8K dataset. We compared different methods such as truncation, sharing, decoupling, and rotation. Truncation resulted in the worst performance due to information loss, while sharing showed better performance by preserving input information through shared rows or columns. Rotation was found to be more efficient than decoupling as it helped the square matrix distinguish input information effectively.